Hey there, and welcome to This Explainer. I am absolutely thrilled to share this topic with you today because, well, it connects the totally mundane to the monumental in just such a brilliant way. We're going to explore the hidden mechanics of solubility. Together, we'll be taking a really fascinating journey. We'll start with something as simple as a glass of water sitting right there on your kitchen counter. And we're going to scale that all the way up to the massive global climate shifts that are actively reshaping our planet right now. By the time we finish up here, I promise you'll see the world, and honestly, your next carbonated beverage, in a completely new light.
Okay, let's dive into this. Have you ever actually tried to see just how much salt you can dissolve in a simple glass of cold water? You know how it goes. You stir, and eventually the salt just stops disappearing, right? It just piles up at the bottom. But what about hot water? Does heating it up change the rules? Well, this everyday, super relatable phenomenon is actually the perfect gateway into the fundamental rules of chemistry that govern our entire world.
To really understand what's happening inside that glass, we need a strict definition. Solubility is literally the absolute maximum amount of a solute, like salt or sugar, that can dissolve in a given amount of solvent at a specific temperature. Now, there are two absolutely crucial variables at play here: the unique identity of the substance itself and the temperature of the liquid. In the chemistry world, we typically measure this precise limit in grams of solute per 100 grams of water. Simple enough, right?
Part 1. Reading solubility curves. Think of this as our mathematical map.
To decode this mathematical map, there are basically three key skills we use to extract the vital information. First up, finding the baseline solubility at a given temperature. You just locate your temperature on the horizontal axis, draw an imaginary vertical line straight up to the curve, and then read across to the vertical axis. That number right there tells you exactly how many grams can dissolve. Second, we use the curve to determine saturation levels, which is essentially just figuring out how full the liquid is. And third, we use these curves to compare different substances, visually mapping out their unique dependence on temperature.
And this brilliantly illustrates how completely different substances react to heat. For example, if you look at potassium nitrate, or KNO3, it has an incredibly steep curve. It becomes dramatically more soluble as the temperature rises. Heat just unlocks its ability to dissolve on a massive scale. But then contrast that with sodium chloride, which is just your ordinary table salt. NaCl has a nearly flat curve. You can boil that water all you want, but it's going to show very little change in solubility as the temperature rises. It simply doesn't care about the heat nearly as much.
Part 2. The saturation spectrum. Let's look at treating the boundary.
So, if a solution's exact state places it perfectly on the curve, it is completely saturated. This means the solution contains the absolute maximum amount of dissolved solute physically possible at that specific temperature. The liquid is totally 100% full. Not a single extra gram can dissolve unless you somehow change the temperature. But what if you aren't perfectly on the line? Well, if you're at a point anywhere below the curve, you have an unsaturated solution. It's stable, and it's hungry, meaning more solute could still easily dissolve into it. Now contrast that with a point above the curve. This is a supersaturated solution. In this state, more solute is dissolved than the curve predicts is even possible. It is an overstuffed, highly fragile, and frankly incredibly unstable condition.
Part 3. Predicting rapid crystallization. Here's where we start manipulating those boundaries. Because these solubility curves are so incredibly precise, we can perfectly predict exactly what happens when we cool a hot, saturated solution down. As the temperature drops, the solubility limit decreases, right? So if the dissolved solute exceeds this new, lower limit, the excess has literally nowhere to go. It gets forced right out of the liquid. The formula to figure this out is super simple. The mass crystallized equals the mass originally dissolved at the high temperature minus the new lower solubility limit at the cold temperature. Okay, let's walk through an actual laboratory experiment step by step to see this in action. Step 1, we take 100 grams of water, heat it up to a scorching 80 degrees Celsius, and dissolve a massive 170 grams of potassium nitrate into it. At this point, it's perfectly saturated. Step 2, we carefully, and I mean very, very carefully, cool this solution down to 40 degrees Celsius without disturbing it. Now, the new solubility limit at 40 degrees is only 65 grams, but we still have 170 grams trapped inside. We have successfully created a highly unstable, supersaturated solution. Step 3, the trigger. We drop a single tiny seed crystal of potassium nitrate right into the liquid.
Now, what's really interesting about this slide is the sheer scale of the reaction. The second that single seed crystal hits the water, 105 grams of solid potassium nitrate rapidly crash out of the liquid, instantly forming solid crystals right before your eyes. No way, right? But the math proves it. Our starting mass of 170 grams minus the new limit of 65 grams leaves exactly 105 grams of excess solute. It's a sudden, super dramatic physical transformation.
Part 4. The rules of gases. Get ready for a major plot twist.
So here's the twist. Gases do the exact opposite of solids when it comes to heat. The temperature rule dictates that gases actually become less soluble as temperature increases. Heat literally forces the gas out of the liquid. But there's a second factor at play here, pressure. According to Henry's law, gas solubility increases with pressure. If you want to force a gas into a liquid, you got to squeeze it in there under high pressure.
And these abstract rules dictate things you experience every single day. Think about it. A warm can of soda is fizzier when you open it because the heat makes the liquid hold less gas, so the CO2 escapes rapidly. On a much larger scale, warm lakes hold significantly less dissolved oxygen than cold lakes, which drastically affects the fish living in them. And the whole reason your carbonated beverages have bubbles in the first place is because factories use extreme high pressure to literally force the CO2 into the solution. When you pop the tab, the pressure drops, the solubility plummets, and boom, the gas escapes as bubbles.
Let's move to and see how this builds. Part 5, Oceans and Climate Change.
Because gases become less soluble as water warms up, our rising global temperatures are creating this devastating, vicious cycle in our oceans. As the oceans warm, their capacity to hold dissolved gas drops. Therefore, they absorb way less carbon dioxide from the atmosphere. This leaves more CO2 trapped in the air, which directly accelerates the greenhouse effect, making the whole planet even warmer. But the CO2 that does manage to dissolve, that causes a second massive problem. It chemically reacts with the water to form carbonic acid, or H2CO3. This actively lowers the ocean's pH, which is a really destructive process known as ocean acidification.
So the crucial point is this. We aren't just looking at abstract charts on a page here. The basic mechanics of solubility, this incredibly precise relationship between temperature, solvents, and solutes, these mechanics are currently rewriting the chemistry of our oceans. As global temperatures continue to rise and the fundamental chemistry of the ocean shifts, what is going to happen to the fragile marine ecosystems caught right in the middle of these changing boundary lines? It's a profound question, and it's one that begins with microscopic chemistry, but ends with the future of our planet. Thank you so much for exploring these concepts with me today.